So in the first version of the program, my title was cut, probably because SMT was not properly defined, but this will be changed in this talk. Okay, so I will talk about Satisfiability Modulo Theories, and so Jason gave quite a nice motivation for this. Well, formal proofs should not be mostly about proving easy stuff, okay? And AI can help us, but also automated theorem provers can help us to prove the easy things for us. And if you are using automated theorem provers, well, you don't have to trust them, so they can give you proofs, as Haniel explained yesterday, or the day before, I don't remember. And those proofs can be replayed within your system, so that means that the ITPs that you are using, the interactive proof assistants that you are using, can replay all those proofs within its kernel, so these proofs are as good as if they were made by the human and went through the kernel. And one example is a sledgehammer tool that allows users to discharge proofs that are from Isabelle into any solvers. I mean, quite a lot of solvers, first order theorem provers, and yeah, other provers like the propositions that also do higher order theorem proving. And one kind of prover that Sledgehammer is using is SMT solver. And one of the solvers is Verity, which is the solver I was working on. So the thing is, the proof obligations that you give to the SMT, to the external SMT solver, might contain quantifiers. So we have to deal with those quantifiers. And this is about, well, this is the topic of this talk. So I will explain a bit what is under the hood of SMT solvers to deal with quantifiers. Okay, so what is an SMT solver? Well, an SMT solver is a propositional solver, a SAT solver, to which you add some modules to extend the expressiveness of it. So a SAT solver can deal with huge formulas in propositional logic, and one very toy example of such a propositional formula is this one, okay? So this is a very easy formula, which is actually unsatisfiable. So the SAT solver would say that this formula is not satisfiable. And then, well, at the beginning, SMT solvers were essentially decision procedure for ground logics. And the first thing you want to add is to have the capability to reason about equalities and some functions that are not defined, basically, so uninterpreted symbols, okay? And you can give that to an SMT solver. Actually, you could give that to an SMT solver 40 years ago, and the SMT solver would say that this formula is unsatisfiable because there's no way to make A equal B, and at the same time have either f of A different from f of B, or QA being true and QB being false. So it's impossible to make it true, so it's unsatisfiable, and the SMT solver would say it and provide a proof for that. And then you might want to extend the expressiveness of the SMT solver by adding more reasoning capabilities, and you might want to reason about arithmetic, so you could have a decision procedure for linear arithmetic and bundle that together with whatever you already have, etc., etc. You can add many more things. And then what about quantifiers, okay? So the quantifiers are kind of special because, well, now, I mean, up to now here, I'm still in a decidable fragment, okay? But when I add quantifiers, well, I slowly get into undecidability. Full first order logic is undecidable. But there's good news. There are good news. First order logic is semi-decidable. So pure first order logic is semi-decidable, which means that there are procedures that would terminate on unsatisfiable problems. And that's lucky for us because what we want is proofs and proofs mean, well, negation is unsatisfiable. So in principle, the SMT solver would terminate on the formulas that we will give it, because what we want is to prove, well, to prove formulas, okay? There are also a nice thing, which is if your formula is not unsatisfiable, so if it's satisfiable but it has a finite model property, well, there are ways to get this decision procedures. But there are also very negative results that Pressburger arithmetic with even one unary predicate is not even semi-decidable. So I mean, if you mix arithmetic with whatever, most of the time you are out of nice decidable fragments or semi-decidable fragments, and that's annoying. Okay. Well, but SMT solver do work, so it means that they manage to deal with your formulas most of the time. And why?
Just ask
yeah,
for clarification.
Sure. Yeah.
So if you have recursively enumerable axioms, then theorems form a recursive semi-decidable set. So this is not what you mean here when you say Pressburger with one unary predicate is not semi-decidable. What is the exact thing that you mean? It doesn't mean given a statement,
no.
does there exist a proof? It means something else.
Well, it means we are working we are working with real world natural numbers, so we don't have an axiomatization.
Oh, okay. You're working in a model.
Yeah.
Okay. Thank you. Yes.
Yeah, I mean, indeed,
Yeah.
there are several ways to seize it. And so why do SMT solvers work? Well, basically because we are giving them easy problems that come from verification. And so the problems that you have in verifications are big, but reasoning, most of the time the reasoning is shallow. You don't have to take a lot of facts and put them together. So these are big problems, but shallow reasoning. And that's why SMT solver, that's what SMT solver are good for. So they are appropriate for long, but mostly ground and uninterpreted function reasoning. So nothing fancy, but they are useful, okay?
What does ground mean?
Ground means without quantifiers. So I will talk about quantifiers, but my basis is that I have some good solvers for quantifier-free problems. And on top of that, I will build something that handles quantifiers. Okay. Yeah, so another working hypothesis in the whole talk, everything I will do is for pure first-order logic, but this works also for the problems I have, even if they do contain some arithmetic and some other stuff. Okay, so how do we make quantifiers and SMT work? Well, first, the basics. So we use the Herbrand theorem, basically, that says that if you have a set of formulas and they are in Scholen form, well, this set is unsatisfiable if and only if there is a finite unsatisfiable set of instances, right? So, and this is my basis. Yeah, and basically this is a fundamental theorem of logic, and this is what we are using always. So sorry if this is trivial for you, but so that we are on the same page, I will take a very small example, very easy example. So we have this syllogism. So all humans are mortals, all Greeks are humans, then all Greeks are mortal. And you can translate that into first-order logic. Okay, so this gives you this. Okay, all humans are mortals, all Greeks are humans, and this is what we have to prove: all Greeks are mortal. Okay, well, it boils down to checking the validity of this formula And since SMT solvers are doing satisfiability, we have to transform this into a satisfiability problem. That means we have to check the satisfiability of this formula, of this set of formulas, basically. And so with columnize, which makes this quantifier disappear. And now we use simply the Herbrand theorem that tells us that, well, we only have one term here. We just have to instantiate all those two formulas by this one term. And if we add the two formulas that are here together with this ground formula here, we're done. So basically the SAT solver, the underlying SAT solver of the SMT solver would be able to detect the unsatisfiability. It's only propositional reasoning now. Okay? Yeah, so we have quantifiers and we go down to propositional logic.
Can you explain this columnize? What is this?
Well, basically, you can invert this. So this universal quantifier is actually an existential quantifier, okay? So not for all means there exists some x such that this must be true, and then you give it a name. So this is not logically, this does not preserve logical equivalence, but this is equisatisfiable. Yeah.
It would preserve equivalence if you had defined S in terms of your.
Yes, I could have defined this S as being the element that make this false. And this would be logically, this would preserve logical equivalence. Okay, yeah. So how does it really work now? So again, I mean, I'm taking toy examples, but remember that the SMT solvers can do that on formulas that are megabytes long. So if you give to CBC very very large formulas like that, it will manage to give you an answer. Okay, so you give the SMT formula to your SMT solver. So let's take as an example this formula again, or no, it's not. This is the first time we see it, but it's a formula like the ones I gave in my first slides. Okay, and what it does is basically it gives it to the SAT solver, but the SAT solver only reasons on things that are true or false, right? So every of those things, like A smaller or equal to B, etc., I mean, they are kind of encapsulated into variables that are true or false. So that's why we denote them by P A smaller or equal to B, and etc. for every of those atoms here. So this is given to the SAT solver, and the SAT solver just have to give a truth value for each of those Boolean variables, basically. And the SAT solver will say, well, basically, you can make this formula true if this is true, this is true, this is true, and this is false, right? I mean, remember, these are disconnected propositional variables. So for it to be true, you also have to concretize them again, and give that to your theory reasoner, and this is the formula that the theory reasoner will get, and the theory reasoner will say, no way, you cannot make all these things true at the same time, because x is equal to 0, which means that B is smaller or equal to A. Since A is smaller or equal to B, it means that A is equal to B, and if A is equal to B, you cannot have f of A different from f of B. So this is unsatisfiable, and how does it say that to the SAT solver? Well, it says, well, now I have a new clause that will give you a better view of the world, and so that I refine the Boolean abstraction, I give that to the SAT solver, and the SAT solver would provide another model, which I don't give here for some reason. No, and this goes down. This goes on and on until either we provide a model or we have a proof. Okay, a proof of unsatisfiability. Okay, so this is my ground solver. And I won't look into this ground solver anymore, but what I would like to do now is to see how to deal with quantifiers. So this is my view of my SMT solver. And now I have a formula that I give to my SMT solver and this formula contains quantifiers. Okay, how will I deal with that? Well, whatever the ground solver can deal with will be dealt with within the ground solver, and this will be again given to the SAT solver. So the SAT solver will have an abstraction of this formula. It will provide an assignment, a Boolean model, and this Boolean model will be concretized. And now it's not the theory reasoners that will complain. It's some other reasoners that will have to reason about the quantifiers and that will have to say, okay, I can make A of A equal B true, S of B true, Q of A false, R of A false. That's not a problem. But I don't know how to deal with this, so that's the theory reasoner that will say this, and the instantiation module will tell the ground SMT solver what to do with this, okay? And what will it do? Well, it will tell us that there's something to do with this, and the thing to do with this is that you have to understand that if this has to be true, okay, it could tell me directly that all this is unsatisfiable, but this is not what's happening. This is too complicated. But it could tell me something, which is more local, which is just that if we have this true, then I cannot have S of A and S of A true and R of A true, R of A false, sorry. So it means that whenever this is true, S of A must be equivalent to R of A. Okay, and that's what an instance does. It tells me a bit more information about the ground. It tells me new ground facts according to the quantified formulas that I have. Okay, and this is the instance that I would generate. I would generate the fact that from this formula I can deduce this ground fact. So the ground solver gives me an assignment, and the instantiation module would give me an instance, which is something like this. So I would add this new formula at the propositional level, and again, the SAT solver would work and would provide me with another model. And if I also provide the quantified formula here, if I also provide this instance that says that if all x is true, then Q of A should be true, then this will ground the problem, basically. So once I have given those two instances, I don't have to think about quantifiers anymore. Okay, so this is how...
You did not yet explain why you picked A, right?
Yeah, that's my question.
You could have picked B, and then maybe it wouldn't work.
Yeah, of course, and that's why, this is the whole point of instantiation in
How?
yes, and that's what I will explain, and that's what I want to have a look at. Okay. So in my context, an instance is basically a formula like this. So for x, phi of x implies phi of, some substitution applied to phi. Okay, so I give some value to all the variables that I have in my formulas. So, and I'm grounding my problems, which means that my sigma here is a ground substitution that associate to each variable some ground term. Okay. So, for instance, if my quantified formula is this one, and my sigma is this one, and my substitution is this one, then my instance becomes this implies this. Okay. And this is tautology. So I can always add tautologies to my formulas. these tautologies help my ground solver and ultimately my SAT solver to understand what I have as a first order formula. Okay, so again, I mean, this works by abstractions and refinements, okay? So this quantified formula eventually becomes abstracted as a propositional variable in the SAT solver. This part also gets abstracted as Boolean combination of propositional variables. But these propositional variables, they do have a meaning at the level of the ground theory reasoner. And they get somehow activated whenever the model is such that for x phi of x is assumed to true. So in the future, I will forget a bit about the quantified formula in the instance, but what I add is basically tautologies, and what I want to find is those, what I will call later instances, okay? Yeah, so there are quite a lot of techniques to deal with instantiations, so to find the right instances, the right A's to substitute the X for.
So if you assume that the for all clause is false, does the instantiation engine suggest an existential element?
Yeah, well, this is about columnization, okay? So this is, yeah, of course, if you know that for x, q of x is false, it means that for some A somewhere, q must be false, right? And indeed, there is some automatic process that will generate new constants.
But some, like when you try to satisfy voice, you have to find the instance of that element, right?
Yeah.
Is that the same engine as the instantiation?
Well, there are cases where finding instances is more. I mean, for columnization, it's just inventing a new term. It's not complicated.
It's the easy case.
Yeah.
You can always do it, and it's straightforward.
No, I'm not talking about the rewriting of the formula. I'm talking about actually like finding an instantiation of the element in the model for this. Like you have to, if it's true, like the existential is true, you have to find some.
One of the theories has to have knowledge on how to do that.
Yeah. So is it like if you want to actually solve a concrete formula, is that like an easy part or?
Well, finding so it's a for all that is difficult. So we're in okay. Probably the problem comes from the fact that we are working in the satisfiability framework. So finding the right instances is for the full quantifiers. So it's for the universal quantifiers that it's difficult. So you have to find the right instances for the universal quantifiers to contradict what you have. So which is the opposite view than the one you have when you are when you are proving validity of things. And instead, when you have to prove validity of something, then it's the existential.
Another way to think of it, an existential variable is the same as just a free variable. So if I have x something, I can just get rid of it and keep the x, and it's just, that's all you have to do.
No, I don't have any problem with that. Like my question is more about like in the algorithm. So okay, so you have a stat layer. Stat layer operates on the propositional.
Yeah.
But the existential is like one level lower. It's in the model layer. You find the element in the model that satisfies this. Right? So it's a different engine that actually handles that part.
Yes, yeah, you're right. But if you find the right instances afterwards, all your theories will be able to assign proper elements to whatever you found. Okay, so as I said, there are several instantiation techniques to generate the instances. And so I've been contributing to some of them, but I will review the major instantiation techniques so that we have a clear view of what exists. So I always cite things. So the slides will be available if you want to get deeper and see who did everything. Everything is, well, not everything is cited, but you have pointers. Okay? So again, we have our ground solver, and our ground solver will provide us with a set of ground literals and a set of quantified clause. And basically what the instantiation module has to do is to generate a certain amount of instances according to the quantified clause and the ground literals that it has, okay? And the classic Herbrand's theorem tells you that, well, if you just generate all possible instances from the set of quantified clause, then you will eventually manage to prove unsatisfiability of your unsatisfiable formulas. The thing is, the set is huge, and we have to find out which ones we want to generate. I mean, it's huge, it's infinite, and we have to make a choice. And one of the first technique was already there in the simplified prover, which was again 40 years ago, and basically it was searching the irrelevant instances according to the terms you already had. So you had a set of triggers, and you are using e-matching to do that. So concretely, assume your ground part is this, so your ground assignment is this, so P of A is false, P of B is false, P of C is true, and R of B is false. And you have a quantified formula, which is for X, P of X, and, or R of X. Well, we can add to this quantified formula. So there are many ways to deal with this. It's just to explain how triggers work. So you can associate to this formula a trigger, which would just be here P of X. And whenever there's a P of X available here, so the X will be substituted by the thing that is available. Okay, so for instance, in our case, we have a P of A, we have a P of B, we have a P of C. So there are basically three ways to instantiate this X with terms that are available in E using trigger-based instantiation. So we have three available substitution, and well, basically you can generate formulas for X equal A, or X equal B, or X equal C, and you see that if I generate the one for B, it will kill my model here. Okay, so it's an ideal instantiation technique for expanding definitions and having rewriting rule and stuff like that, because it concentrates on the things that you have available in your ground part of the formula. So, for instance, if I have this set of formulas, I have a definition of what it is to be sister of what it is if X is the sister of Y. Okay, I define it like this, and then I have a few facts like Eliane is the sister of Eloise, and Eloise is the sister of Elizabeth, and I also ask myself whether it's satisfiable with all this to have that Eliane is not the sister of Elizabeth, and if you have a trigger that is associated to this quantified formula, and this trigger is sister X of Y, whenever I see a sister XY in my ground part, I will generate the corresponding instance, and for instance, I will instantiate this formula with Eliane and with a pair Eliane Eloise, Eloise Elizabeth, Eliane Elizabeth, and quickly find out that there's a contradiction. But at the ground level, I will not have to reason about quantifiers anymore. Everything will be down to the ground level. So yesterday, somebody asked, or when Haniel gave his talk, somebody asked whether you could add your own decision procedure into an SMT solver. Well, triggers are a way to to have your decision procedures. I mean, not everything goes into triggers, but there are some things that go into triggers. And for instance, you can have a series of arrays or a series of lists that would be modeled as a set of axioms, basically with carefully designed triggers so that the ground instances are generated as we want to have a decision procedure. This is a technique which is mostly efficient, and this works well in practice, but it can also blow or miss the right instances very easily. So there are other techniques that we will need. And it requires triggers, so we need to find a way to associate to every formula some triggers, so some things, some terms that we will have to look for in our ground magma to generate new instances. And having those triggers requires either human intelligence, so that you will put the triggers manually to the quantifiers, or they have to be auto-generated, but that's, this can be done. Yeah, we can do it, but maybe not in the best fashion. So here we have an opportunity for improvement. So the number of useless generated instances is great. I mean, it's huge. In many cases, you can have hundreds of thousands of instances that are generated by matching or other techniques that you will see later. And at the end, if you look at the prune proof, there's only 1% of them that you are using. So basically, you are generating a lot of instances. You are generating a lot of work for your grand solver, and at the end, you throw away most of them. So there's a lot of opportunity here, and especially for machine learning. So can we separate the wheat from the chaff and select the useful instances? And we have been trying some things there. So we investigated XGBoost to filter instances. And yeah, it has been, we train the technique on successful proofs, so the proofs that we can do. And what we call a good instance is the one that survives pruning of the proof. So we take the proof, we eliminate whatever has not been used in the proof, and whatever remains is what is useful. So that allows us to tag instances with good instances and bad instances, and this is used to train the model. And this is what we get. So if we take Verity, the vanilla Verity, we manage to solve within a certain time a certain amount of formulas, and every time we train the model, we manage to solve a bit more and a bit more. And when we take all those trained solvers together, so we have a portfolio. Portfolio work well in SMT. So we try many things together. We manage to improve quite a lot. This solver, which is, reasonably good, but not extraordinarily good if you compare to state of the art at the time of this experiment, which was CVC4. Okay, so there's still a lot of improvement here, and we have to find, AI can help us, but we have to have techniques that are very, very quick, right? We are generating tens of thousands of instances per second, and we have to eliminate them quickly, okay? Yeah, and so if you see, with filtering of instances, basically we managed to cut by 2 the number of instances. I will not go into too many details here. It doesn't matter.
Is the benchmark set computer science style or math style?
It's I'm afraid it's mostly computer science. Yeah, mostly verification. Yeah, of course.
That who pays you, so it's okay.
Yeah. Indeed. Mm. Yeah, I mean, there is hope that sometime, I mean, or for some easy stuff, it will be useful for math. So again, among the benchmarks that we have, there are things that come from Sledgehammer, and in Sledgehammer, there are also some things that are somewhat related to math, but it's not mainly math. And what is called math in Sledgehammer sometimes is also verification in a sense. Okay, so another quite useful technique, I mean, a very useful technique, is conflict-based instantiation. And basically, what we do is we search for one instance of one quantified formula that is unsatisfiable together with the ground stuff that we have. So basically, if you have this as your ground model or ground assignment, and you have this formula, so this is probably the same example that we had before. Well, you can directly see that if you instantiate this x by b, then you directly kill e, right? So this conflict-based instantiation technique just will simply return the instantiation that assigns x to b. And how do we do? Well, we have to solve this problem basically. So we have to find a sigma such that psi sigma with E is unsat, where the psi that we have comes from some quantified formula. And this comes to finding a sigma such that the negation of psi is entailed by E. And basically, if we have E, which is this, and Q, which is this, that means that my psi is just this. You would transform it into this problem, and we ask ourselves, what is the right sigma that I have to have here, so that this is a logical consequence of this? Well, f of x has to be equal to f of z. So there are several ways to do that. Either we make x and z equal, so we say x equals z. But there's another way. We know that f of a is equal to f of b. So if x goes to a and z goes to b, then we can also find maybe a solution, or the other way around. Okay. So first, we try to make f of x equal to f of z according to what we have here. So these are the possibilities. And then we try here to make h of y different from g of z. And how do we do? Well, there's only one possibility, actually. We have to make z equal to b and y equal to c. And then we mix everything together in some way, and we get some substitution. So this is one substitution, and this is another substitution that we get. Okay. So this seems pretty easy. Well, it's not completely easy. So this is our problem. And it's a variant of classic rigid unification. It's NP complete, so it's kind of hard, kind of easy to show that it is NP complete, because it's in NP because the solutions can be restricted to ground terms that we have, and it's NP hard because you can reduce 3SAT to it. And Haniel and Andy and myself worked on some techniques to solve this problem efficiently. And there's a sound complete and terminated calculus, which is called, and the problem is called CCFV, and also the calculus that we use to solve this problem, we call it CCFV algorithm. It's goal-oriented and it's efficient in practice, but it takes us still quite a lot of time, so we are looking for better ways to do that. But just to give you an idea of how strong this conflicting-based instantiation is, so this is CVC. This is some work from. This is some. I stole this figure from Andy in the CVC team. So Andy invented the conflicting-based instantiation, but not the CCFV algorithm. We came up with this algorithm later, and this is what brought the first version of conflicting instances to CVC. So each time you have a dot below the line, below the diagonal here, it means that the new version of CVC with conflicting instantiation is better than the older one, and you see clearly that using conflicting instances make CVC incredibly better for dealing with instances. And when we use CCFV, well, it made CVC again a bit better, and Verity much better. Okay. So there are still a lot of things to do there. So 60% of the time of Verity is spent in this algorithm, which is quite a lot. And as I said, CCFV is an NP-complete problem. It can be encoded into SAT. So we are using SAT again well, we plan to use SAT again in the solver. And we want this to have a more efficient procedure. And we also targeting more expressive logic. So we want to go from quantified logic to higher order logic in SMT. And this is also, well, an opportunity here because a SAT-based CCFV algorithm would simplify the CCFV algorithm and give us more power to attack higher order problems. Okay. Yeah, another prospect is conflicting instances work really, really well, but only for one instance and one substitution. So could we find out a way to extend that to several instances to contradict just one model? And we plan also to use superposition inside the prover to extend the algorithm to find conflicts with several clauses. I will go quickly over model-based instantiation. So basically, we want to build what model-based quantifier instantiation, which is a technique by Gay and Demora, who was working in Z3 before working on Lean. So model-based instantiation is a technique that basically builds a model for the ground stuff that you have and check if this model is current with the quantified formulas that you have. So for instance, if you have, again, this set of ground stuff and this quantified formula, so from this, it will extend the model, it would create a model, and this model would make P true for whenever x is equal to c, okay? So it has to make P true for x is equal to c, P of x true for x equal to c, and it makes P false for all the other cases. And the model would make R false everywhere because R false everywhere will be consistent with this, okay? So this is a model that would be extended from whatever I have as information here. And then you check this model against the quantified formula, and you quickly see that, well, in the case of x equal a, this is not made true by my model. So this is actually, well, this is contradicted by my model. And so you want to make your ground part more consistent with your quantified part. So you would add a new instance that will tell you that you have to have either P of A true or R of A true, and that will feed your next try, that will feed your next E for the next round, okay? ITE is if then else. So in the case of x is equals to c, then it is true. In the case of x is different from c, it is false. Okay. Model-based instantiation is really nice. It creates a lot of instances, but it helps you to find models when you have some models and when you have a finite model in particular. But there is still a lot of space for improvements there too because of the number of instances it generates. So another technique we worked on was enumerative instantiation. And enumerative instantiation is, again, taking the Hilbert theorem, but directly in a straightforward way. So actually, 50 years ago, the earliest theorem prover relied on the Hilbert theorem for instantiation. But at that time, computers were not good enough to handle the many instances. It turns out that now we can revisit this, and it actually works pretty well if you are careful with the way you enumerate instances. And that's what enumerating instances is about. So I will go quickly over this because it's kind of boring. Because the thing is, you take whatever you have in the ground solver, look at what terms you have, generate instances in a fairly systematic way, and you hope for the best. But the best often comes. So I won't go into too many details. Again, you have many possibilities, and the thing is, you have to choose the right possibilities. Okay, so it happens that enumerative instantiation plays kind of a similar role to model-based quantifier instantiation and can serve as a completeness fallback to conflicting-based instantiation and trigger-based instantiation. Okay, so those two techniques that I saw before, they were essentially incomplete. They were working quite well, but they were incomplete. Model-based quantifier instantiation, as well as enumerative instantiation, makes the system complete for pure first-order logic. So enumerative instances has some advantages over model-based quantifier instantiation for unsatisfiable problem, and it's significantly simpler to implement. So prospects here, and again, I will skip all these technicalities. It doesn't matter. The thing is really how do we enumerate those instances, because we have many of them. And yeah, I skip this. There's a lot of improvements. There's probably a lot of opportunities here also for AI to choose the best way to generate this stream of instances. But again, it's for future work. We have also some works in those directions recently. You can have a look at this if you are interested. Okay, so experimentally, what does it give? Well, so again, thanks to Andy for this. This is Andy Reynolds in the CVC team. This is just pure model-based quantifier instantiation. This is enumerative instantiation. This is trigger-based instantiation. So you see, this is the number of problems we tackle within a certain amount of CPU time. So, the lower the curve is, the better it is. Okay, so each individual technique allows you to solve a certain amount of problem within a certain time, but the best result you get is when you mix them together. And what we get here is trigger-based instantiation with enumerative instantiation that follows. So this is the best technique for something like 200 seconds.
You literally need to do one, then the other, then one.
Yeah. So when one fails, you take the other.
It's
a green one, and you interleave.
It's similar to the orange brown
Yes, I mean, the more problems you solve, the more difficult it gets to get a few more. So that's the thing. You have the impression that this is good enough already, but what you want is the formulas that are in between. And even if this is just a bit better, then it's good. Also, if you mix the techniques together, so if you have several solvers that do different things, you might also get some more out of it. So. Portfolios really work well in SMT. Okay, and well, it happens that model-based quantifier instantiation is still very, very useful for satisfiable formulas because it actually provides models. Okay, so I'm reaching my conclusion here. So the quantifiers in SMT are handled in a very ad hoc manner. And well, the techniques that we have are essentially targeted to target pure first-order logic with equality. So we don't really have a lot of theory reasoning, strangely enough, in the SMT quantifier reasoning. So there's also a lot of improvement, a lot of space for improvement here, but they are reasonably effective nonetheless. So in the future work, well. Instantiation techniques will I guess, improve a lot in the future for SMT. There's a lot of room for improvement in the vampire world. So yeah, you will talk about that probably tomorrow. They have this attitude that they take one problem, try to find the technique that will make it tractable for the solver, and add the technique, and then all those techniques group together to make a powerful solver. In SMT, I mean, CVC people do have this kind of attitude, but maybe not as strongly as the vampire people have, and maybe this would also help us to have even better solvers in SMT. Machine learning is an opportunity, but we are working on like tens of thousands of problems per second. So we need to find techniques that are very quick to help us. And I mean, they can fail. They can discard things. Well, maybe not discard, but they can let things go through. It doesn't really matter much, but they have to be fast. We expect more conversions with state-of-the-art first-order theorem provers that are based on saturation. And yeah, there is quantifier elimination for some theories, like Pressburger and so on. These are not really well integrated into this, so there's a lot of things to do there. And higher-order logic. So we are currently working hard to make all this work for higher-order logic in order to have more expressive.
High-order logic, you just mean literally classical high-order logic?
Yes, yeah. Okay, thanks.
Thank you.